For Lab 5, I chose to analyze the motion of a kicked soccer ball because I've played my whole life and am interested in exploring the physics behind it. My objective here was to analyze the motion of a soccer ball kicked in a parabolic arc by creating a computational model of the ball's position using Newton's second law and comparing it graphically to the observed position in Tracker. I will also be determining if a computational model with a drag force is more accurate than a model without. I will then make a graph of the kinetic potential, and total energy of the ball to show that the energy principle was in fact preserved. My results were that I found that the model with drag more accurately described the observed ball's x and y position, and the energy principle was preserved because E total on my graph was 0. Fundamental principles needed in this lab were Newton's second law, which is also the momentum principle, and the energy principle. Newton's second law is change in momentum equals F net times change in time, and therefore we can rearrange this to be Vf equals Vo plus F net divided by mass times change in time. Now for the energy principle, if the ball is my system and there are no interactions with any outside forces, then the total energy is 0, meaning that kinetic energy plus delta potential energy is 0. Now for forming the model, I had to do some basic initializations like we do in Tracker for every lab, with the mass of the soccer ball, calibration stick, being the diameter of the soccer ball, and my axis being in the negative x and positive y direction. I also found VO by taking my final position minus my initial position and dividing by my change in time, which is about 0.033 seconds. Now for finding position at each different delta t, I used Newton's second law, which is Vf equals Vo plus F net divided by mass times change in time, to find my new final velocity at each given delta t, and I used that final velocity in the position equation, Rf equals Ri plus Vf times change in time, to give a new position. This is all in a while loop for every change in time up to when I want to stop my loop, so it ends at about 0.9 seconds and gives me position for every time. So now for finding F net, once the ball leaves my foot, the only interaction in the system is with gravity, which is in the negative y direction, and drag, which is actually in the positive x direction because it's opposing the negative x position direction, and the negative y direction, so that's actually a typo right there. And where I have F drag written here, I guessed and checked between my output model to see which model would give me the best, and negative 0.6 and negative 0.5 worked, and that's actually 0.6 because I changed it later. So F net equals F grav plus F drag. Now as you can see, this is the model without drag force, where the blue ball is my computation model and the red ball is my observation. You can see that the blue ball, which is the computational, doesn't really depict the observation as well. But the model with drag force depicts it extremely well, where my error is probably in the observation not completely matching because of my point mass placements on Tracker, which I couldn't really see the ball throughout the entire motion, so that's very common. I also placed some arrows here so you can see some forces. This is the F of gravity, and this is my resultant velocity. These are my results plotted because I outputted my model to a CSV file. My orange is the observed x position, my black is the model with drag, and my blue is the model without drag. And you can see that the black points and the orange points match up really well, which shows that as a result, the model with drag was more accurate. Now for finding kinetic and potential energy and satisfying the energy principle, I first had to found initial kinetic and potential energies, which kinetic is 1/2 mv squared and potential is mgh. So I first found those initials, and then in a loop of change in time, I found my kinetics, and then I just subtracted to find my delta k and delta ug. Then I added them together and then plotted that. Down here you can see this line of code, and we should get 0. And as we see, the green line is E total, and it is in fact at 0, where the red line is K total and the blue line is potential energy. So this graph does conserve the energy principle. This makes sense because at the beginning the ball only contains kinetic energy, so no altitude change. But as the ball moves in the positive y, the kinetic energy decreases while the potential increases because of the altitude change. So an inverse relationship is depicted, and this is a very ideal graph. Now, what does this mean? For my system, was the energy principle satisfied? Yes, because the green line, E total, was 0 on the graph. If the force of gravity and the initial kinetic energy of the ball is the system, then there are no outside forces acting on the system, and delta E is 0. Now, what if the ball was not uniform, as was assumed? The drag constant would be larger because the sphere is not streamlined and uniform in the air. If we actually calculated the drag constant instead of just matching like a guess and check, then we would have to create an equation accounting for the extra drag on the non-uniform ball. Thank you.